All right, thank you to Marta on that. You can lump us, Michigan, into that. We're actually going to bug Cornell here later tonight, asking about that. So, all right, our next presenters are going to talk about the new North Carolina DOT hydroplaning policy, analytical tool development, and mitigation strategies. So we have three presenters here. So our first presenter is Matthew York. He joined the North Carolina Department of Transportation in 2013 after graduating from North Carolina State University. Matthew has nearly a decade of experience involving transportation drainage, H&H modeling, drainage design, permitting, and drainage design guidance. In 2019, Matt began efforts to bring hydroplaning analysis up to date with the latest research and tools available and created a multidisciplinary hydroplaning technical advisory group for the department. Through these efforts and the partnership of Atkins Global, the hydroplaning analysis tool and guidance is ready to address safety and resiliency of major transportation facilities throughout the state. Katie Earp joined Atkins in 2020, bringing 17 years of water resource engineering experience involving transportation drainage, H&H modeling, floodplain mapping, drainage design, and permitting efforts. Katie served for 7 years in the Florida DOT Central Office Drainage Group. She worked on many innovative water policy projects while at Atkins, including NCDOT's hydroplaning program, FDOT resiliency efforts, and regional watershed management policy. Rick Renna was born and raised in Key West, Florida. Jealous. Moving later to the Fort Lauderdale area, where he joined the Florida Department of Transportation, FDOT, in 1974. He served in construction from 1974 to 1986 as an estimates engineer, segmental bridge inspector, and construction project engineer. He managed bridge scour research from 1988 to 2010, including the development of FDOT's bridge scour equations. Rick served as FDOT District 4 drainage engineer from September 1995 to late 1998, the FDOT state drainage engineer from 2001 to 2016, and joined Atkins in 2016 as a senior water resource engineer. Both at Atkins and FDOT, Rick has focused on stormwater management process and BMP development, bridge scour, pipe service life, coastal engineering, major highway and regional drainage design, bridge hydraulics, and hydroplaning analysis. Please welcome them.
Why is this not on? It's not on. I thought this slideshow's not running.
No, it's not. It's weird. You're not in presenter view.
It should be in present.
I can't see well enough to hit this little thing right there.
Yeah, there you go.
You know, folks, I don't know what to say.
What's that say? Zoom slideshow?
Might be pulling it to a different window.
Oh, it's still pulling from hers.
Oh. There you go.
Go ahead.
There we go.
Yes.
Okay.
Yay.
Hi, everyone. I'm Matthew York. I'm from the North Carolina Department of Transportation, and we're excited to be here to talk to all of you about our new analytical tool, our policy that we've recently come up with, and a future preview of our mitigation strategies that we're coming up with, the mitigation selection guide. So just what we're going to be covering is just a brief history of how we got from 2019 to here. Talk about our program advancements, show you some images of our hydroplaning assessment tool, which after we're done meeting today, we will set up a computer out there to show you the tool if you want to look at it. And so there's that. And then also we're going to show you a preview of our mitigation selection guide. So when we're talking about hydroplaning, we're talking about hydroplaning on wide typical sections. We're not talking about ponding along a curb. And so why are we addressing it? You know, it's a safety concern. We have a lot of high-speed facilities that are only getting wider and wider as populations increase in all these cities. And so, but there's also new mitigation strategies that we can use to help mitigate for hydroplaning potential. So in 2019, I was reading an RFP for design build, and we had put, hey, we need you to do an assessment on hydroplaning. And the consultant came to me and said, what assessment? What guide? What do we go to? And we had listed 4 or 5 different things. We said HEC 22, the AASHTO drainage manual, Georgia DOT's tables, or Florida DOT's hydroplaning tool. And so when they asked about it, I dug deeper, and none of them really gave us an equation or a way to calculate it, except for Florida DOT's. So what we did was we developed a template that the consultant could run the computations, provide it, and put down mitigation for hydroplaning. And so that's how it kind of started. But we realized that it's more of a group effort. It's not just a hydroplane, it's not just a hydraulics issue, it's a roadway issue, it's a maintenance issue, a construction issue, it is a materials and testing issue, and so we knew that we needed to broaden the group. So later that year, we developed a hydroplaning technical advisory group, which we met and we still meet quarterly, or even sometimes more than that, depending on all the policy that we come up with. And so really we're trying to make the whole department look at safety and mitigation for this problem. And so in 2022, we just came out with new guidelines this year, and in Chapter 4, we cover a lot of this in Section 4.3 of our guidelines, talking about hydroplaning, how we came to our conclusions, what to be looking for. And recently, we just published a hydroplaning assessment tool. And Katie will be showing that here briefly in a few minutes. But we're also looking to do future research. We're not stopping here. We're wanting to look and find out more. You know, all we've done so far is just taken existing data where we could find it and just brought the tool up to date based off FDOT's original stuff. But we know we need to do more research. We need to even redo the calculations. And also look at driver speed reductions under different types of pavement. So there's a lot of different things we got to look into. So here are some of the program advancements that we've done for hydroplaning. So we've adjusted the hydroplaning speed for modern tires. We've also modified the pave drain hydroplaning speed equation because we found a discontinuity. Also, we have looked into a calculated super elevation water film thickness based off Charbonneau's work. Also, we've already got the tool out, and soon we'll have a mitigation selection guide. So these are the tires that were used originally for hydroplaning testing. You can tell they're not your normal tire. They don't have any tread other than the ribbed tread on the ASTM 501. And so all this information and all this data was pulled off these tires in the 70s. And I think it's time to bring things up to snuff. And so, you know, Galloway, he used the ribbed. Agrawal used the pave drain. You know, he's the one who created pave drain, and he used the flat tires. NASA also used that. And so they also looked at tire pressure of 24 PSI back then. I don't know how many of you have had a a tire light on at 24 PSI, but I have. We actually looked into tire pressures for modern cars. Even back to 2005, I was looking at Toyota Corollas, everything. And so we went based off of what the recommended tire pressure was for the car. And even that was 30 PSI. And so we thought, we need to adjust it for the tire pressure. And so Ong and Foy did some modeling based off Galloway's work, and the 2012 report that Gujaratni did for FDOT, he took their information and plotted it. And so this is basically a tire load of about 1,000 pounds, and they show a 24 PSI and 29 PSI. And the speed at which you begin hydroplaning was actually 5 miles per hour greater with a 29 PSI than a 24 PSI. And if you had an even more tire pressure, it was an increase of over 12.3 miles. And so we thought we needed to do an adjustment. So we thought we would go with 29 PSI. We did find maybe 1 or 2 vehicles that are recommended at 28 or 29 PSI. I think it was the Mini Cooper and the Volkswagen Beetle, but the majority of all other cars are all having recommended tire pressures more than that. And so that's why we've added this adjustment. So now I'll let the, uh-oh, is it not going? Oh, there's a 5 mile per hour. All right, I'll let the legendary Rick Renna come up here.
You know, I swear there must be a sign on my back that says, go ahead and abuse me. Okay, so I know things will happen when I press these buttons. I just don't know what. It looks like forward and back. Is this little guy in the end the laser pointer? No. Maybe this is. No? Oh, well.
Go ahead and just tell me advance.
Okay, that's okay. I think I can get into advance. Okay, so we're going to dive a little bit deeper at this point into some of the technical issues. But out of mercy on our audience, how many of you have seen these type of equations, have seen definitions of water film thickness, hydroplaning speed, knot spread, knot skid resistance? Okay. How many of you all have seen this? Anything like this? Okay, a smattering. Okay, well, we thought it might be the case, so we're going to go into some of these definitions. But this is the current equation, published, paved drain, excuse me. Notice the fixed boundary over here at 0.094 inches. There's a forced jump between 2 equations, maybe. Maybe. Okay. I'll just mash these things when I want to. Okay. That's okay. One is the Agrawal equation. Agrawal is what you use if your water film thickness is less than 0.094 inches. And the next equation, thank you, Vanna. The next equation is the Galloway equation, which you use at greater than or equal to 0.094 inches. And notice this MTD term. Notice that you do not find it in the Agrawal term, but you find it in the Galloway term. This Galloway term is on this side of the comma is a comparison of, that's one term without an MTD. On the other side is an MTD term. And as the MTD gets greater, the mean texture depth, thank you.
It should work now. It wasn't plugged in.
Yay. As the mean texture depth gets greater, this, do I dare press something? I think I should try a different button. Okay, so I'm actually afraid of this now. Eesh. I'll try a different button. It might not be any better, but it'll be different. So here are some of the terms that were in the equation. First of all, no. The red line is, oh, yay. Okay, so for a given water flow, say at 2 inches per hour or 3 inches per hour, 1 inch per hour, you have a given flow coming off of your pavement. And the flow above what we call the riding surface right here is called the water film thickness. That's what your tires see. The treads in your tires are intended to shed that water so that the water doesn't go underneath your tire and lift up your tire, and that's called hydroplaning when you lose contact with the pavement. So as pavements are improved, more volume is able to be held below the riding surface, and the water film thickness gets more shallow. That's called a safer situation. So, no.
I'm here just in case.
I just wanted to advance. There we go.
Okay.
So, let's go back here for a moment. Remember hydroplaning speed, right here, yay. Hydroplaning speed is the speed that a driver, at least computationally, can go and have a negligible chance of hydroplaning. It's a safe speed. So we want drivers to be going less than the hydroplaning speed, or if they're going to speed, we want to do something to bring that hydroplaning speed up to where they don't spin off the road, right? Okay, so when the equation was created, when the paved drain equation was created in 1986 by a guy named Hubner, open graded friction course, which is what this stands for, it was around, but it wasn't in prolific usage. What's called hot mix asphalt or dense graded asphalt concrete was the dominant asphalt. It had fines. It was a structural asphalt. And when Hubner created this in 1986, this curve came along and just went happily onward, and that represents an MTD of about 0.28 approximately. But as pavements improved, and we saw a much significant greater mean texture depth, that is the storage capacity beneath the riding surface, the equation didn't recognize it. Remember that Agrawal's equation didn't have an MTD term. So you can improve the pavement all you want, and the equation doesn't give you better results. However, Galloway's equation did, but you couldn't get to Galloway until 0.094. So what you have right now in the current equation is if you have a good pavement with some storage in it, it suddenly jumps up because it has to wait to 0.094. Well, that's an easy fix, right? What we did, there's the old equation. Again, notice that MTD is only here, and it's forced at 0.094. Just got rid of the force. Okay, nothing changed, except that we allowed the equations to meet naturally. And so now you have Agrawal versus Galloway, and without telling it where it's going to jump. So what you end up with is this. You end up with a family of curves where the Agrawal equation is down here, and where you have a low MTD, it just continues. But as the MTD gets greater, the Galloway equation kicks in earlier. Okay, the natural extension of Galloway's equation hits at the Agrawal equation, and this can be significant. For instance, it was 0.067, so it's halfway or so in between here. The open graded friction course now comes along here. And if you've got a water film thickness of about maybe 0.07, 0.08, you can see that you're looking at, say, 55 minus 61, 6 miles per hour increase. That's a lot. That's a lot. So the only difference is that by turning loose of the 0.094, you now get credit for the improved pavement. It's pretty simple. We didn't tinker with the equation. We just kind of let it do what it could do. This wasn't Hubner's fault. He did a great job for 1986 and for the pavements that were there. Nothing the matter with what he did. Okay, super elevation transitions. A normal flow path on a tangent section, where it's not curving, where it's not going to super elevation, looks something like this. But in a super elevation, the pavement begins to flatten, rolls through a zero cross slope, and then now it's sloping again to the inside. This is the outside. There's a happy inlet. And so with this long flow path, you accumulate a lot more water film thickness. The residence time of the flow on the pavement is significantly greater. Our equations don't handle that. Paved drain was never meant for that situation, at least the paved drain equation. So fortunately, Dr. Randy Charbonneau in Texas and for TxDOT did some great research. It appeared to be very thorough with calibration. He used the diffusion wave model. You can see the multitude of roadway widths he looked at, the multitude of slopes, the multitude of rainfall intensities. He looked at coming into a super elevation, a type 1 he called it, and coming out of a super elevation, a type 2. Very, very thorough. And so we thought, well, we can use this. Interestingly, he found out that at fairly low longitudinal slopes, you get a maximum water film thickness out near the outside, which is what you expect on a tangent section, right? But as the slope steepened, that maximum location began to move inward, and as it got very steep, it moved very inward. Again, very different behavior than a tangent section. So what are we going to do with this? Well, what we decided to do was create a super elevation factor where we took Charbonneau's water film thickness and divided that water film thickness by the computed tangent water film thickness of the section that he started with. If he started with 4 lanes like this, and then he went like this, and he gave us a maximum 4-lane section, 4 lanes in one direction, we took his maximum and divided it by the tangent section maximum that he started out with. In other words, we normalized the increase by what he started with, okay? And then we multiply that by whatever section we're analyzing to get an estimate, hopefully a conservative one, of the super elevation water film thickness of the section that we're trying to design for, okay? And we went through all of the slopes that he did, all of the lane widths that he did. We curve fit down. Remember, he did 4, 6, 8, and 10. We curve fit it down to 2, and we'll show you why in a moment. And remember that water film thickness location, the maximum water film thickness location, very dependent upon the longitudinal slope of the roadway. So therefore, whatever water film thickness, and this is NCDOT policy, I'm stating their policy, whatever water film thickness is shown to be the maximum by this approach, we assume that it could happen anywhere within the transition. Okay, because it could. The truth is, it could. Now, the reason that we ratcheted it down to 2 inches per hour was some good work by FDOT, which NCDOT is hoping to do for the way North Carolina drivers, who are more civil, tend to drive. If you've ever been in Florida, you know, just avoid Tampa, just southeast Florida, Jacksonville. They fly. They don't slow down in rainfall. And so this column here is increasing rainfall. Sane drivers decrease their speed during heavy rainfall. 45 miles per hour is a default to show that we're really not expecting hydroplaning when people should be pulling off the road at 3 and 4 inches per hour. And so we found, just through different work at FDOT and then later on at NCDOT, that 2 inches per hour is where the decreasing driver speed, decreasing from design speed, and the increasing water film thickness tend to meet. Now, we were interestingly surprised that in mountainous North Carolina, where you have greater slopes, we were finding in some cases 1 inch per hour was the critical. A bit of a surprise, but that was okay. So, here are the factors. Remember that these factors are the water film thickness divided by the tangent water film thickness, the maximums of both. And what we found, and this, we were surprised at first until we thought it through a little bit, was that increasing laneage results in decreasing water film thickness factor. And the reason for that, remember that the factor is the super elevation water film thickness divided by the tangent water film maximum thickness. And the tangent water film maximum thickness in the denominator is increasing at a greater rate than the super elevation water film thickness. Therefore, the factor is going down even though the maximum water film thickness is going up. Okay, everybody okay with that? We also found, and you can see it over here, notice how this is dropping off on both sides. Okay. We use these peaks. We didn't try to discriminate between different longitudinal slopes. We just took these peaks, wherever they might occur, the maximum for each one, like over here and then over here. And this became our 2, 3, 4 lanes and greater than 4 lanes in one direction. Because increasing laneage results in lower water film thickness factors, we can just use the 1.3 that we got from Charbonneau, from Charbonneau's work, because he stopped at 4 lanes. So we're stopping at 4 lanes. We can just conservatively use that. If it happens to be 1 inch per hour is critical, we found that the water film thickness decreases with lowered rainfall. So to use 2 inch when it's really 1 inch, still conservative. Okay. So I'm sure there's questions, so we'll catch them at the end. And at this point, Katie is going to tell us about the cool tool. That kind of rhymes.
Cool tool.
The cool tool.
Okay.
And thank you, Katie.
Thanks. I just got the 5-minute mark, so I am going to go pretty quickly here. But and I'm sure there's lots of questions we can hold till the end. So all the hydroplaning improvements that we've talked about to date, the super elevation, the discontinuity, they've all been integrated into this new NCDOT hydroplaning assessment tool. NCDOT's tool is based on the foundational engine from FDOT's program, and modifications have been made to North Carolinize it and align it with North Carolina's hydroplaning policy and program. NCDOT is very grateful to Florida, and Jennifer Green in the back there, for all the research and information sharing that has allowed them to advance their hydroplaning practice. We're now going to quickly run through a few of these highlights of the program. Before I leave this slide, here is a link, very long link for where you can download the program. There's also an example there to help you get started. Okay, so what is this tool? This tool is essentially a spreadsheet that allows the designer to analyze a typical section that might be of concern or different areas of concern, say a super elevation, within your design. And here are some basic highlights for this. This one here, this duplicate scenario button is that, I think, one of the biggest improvements. It's a huge time saver. If you've got multiple different typical sections you want to look at, multiple areas of concern, this lets you duplicate the data. You can analyze lots of different areas right in one Excel sheet. It's a big time saver. Up here is just the area for general inputs. There's now a drop down for your final pavement surface layer. Note at the bottom here, and all of these have been updated for North Carolina specific pavement textures. There's also a user-defined option, so if a designer wants to use maybe a non-conventional pavement surface, they can select this and enter their own MTD. And there's a geometry interface here, so basically putting in your cross slopes and your slopes, and you have a little nice graphic here, and that changes it around. All right, so here's a screenshot of the results. This is the worst case scenario, which is automatically identified by the program and reported to the designer. And here I should note the water film thickness that is reported is the average of the 4 national water film thickness equations, which is the NCDOT policy. That was another change to the program. But if the designer wishes, they can scroll down and they can look at all the different data. So water film thickness, driver speed, hydroplaning speed for all the different lanes, all the different intensities, it's all there. When super elevation is selected, you enter in the lanes, it gets factored like Rick was just discussing, and then the results are produced. And as Rick mentioned, this maximum water film thickness is presumed to occur anywhere within that super elevation transition. And this tool was really developed with NCDOT's production program in mind. So this feature here allows the designer to take all of those iterations and design and analyses that they've done within the Excel program and export them to a final assessment table. I know this is hard to read, but it's very cool. It has all of your data set here. You can analyze a section. So say at the top here, you've looked at something. It's not looking so great. It's looking pretty yellow. You can duplicate the scenario, apply a mitigation strategy, see how it works. Does it get you a little further in the green? Here it gets you a little green, yellow, and you can, all this data can store right here. You can export it for ease of review and document retention. It's a neat feature. Okay, so pivoting to the upcoming mitigation selection guide. As Matt mentioned earlier, hydroplaning is really a multidisciplinary issue and needs a multidisciplinary solution. So this guide will assist the project team through different geometric, pavement, and signage options, depending on what type the project is, if it's a design job or maybe it's a maintenance job. This framework here is just for design, but there is another one for maintenance. And the type of job is important because, for a design job, when you're coming in fresh, you might have more geometric mitigation strategies available to you. Whereas in a maintenance project, you may not have a lot of geometric mitigation available. You might be looking at pavement or signage or things like that. So it helps the project team navigate through and find the most appropriate strategy for their design scenario. And the mitigation selection guide focuses on 3 main buckets. First bucket being your geometric mitigation strategies, things like reducing pavement, flattening longitudinal slopes, increasing cross slopes, and possibly even using a staggered superelevation transition. The second bucket is your pavement mitigation strategies, whether you need to add open graded friction course or possibly ultra thin bonded wearing course if you're in ice and snow conditions. We've also included grinding grooving, shot blasting, and high friction surface treatment. The third bucket is driver behavior strategies and signage, which can actually be surprisingly effective. This includes static and dynamic signs, lower and variable speed limit signs. And NCDOT is also looking at in-vehicle notifications. So we all have in-car GPS systems, as well as Google and Waze and things like that. So, what is the possibility of actually, when a car is on a road and a place that is known to have, hydroplaning accidents and there's a 2-inch rainfall event, well, why can't we send alerts to drivers to let them know to slow down? So that's something we're looking into right now as well. So going back a few slides, this is the framework for this guide, and each of these little boxes is a strategy. And so when this product is complete, which will be soon in about a month, you can kind of click on any of these boxes and it'll send you to this, which is basically, this is sort of a blow up of the groupings here, but it's a strategy information sheet that gives you sort of everything you would like to know about that mitigation strategy. A description, pictures, design considerations, what the expected mean texture depth would be, how do you need to maintain it, the cost, and really, how is this even going to help me with hydroplaning? Does it get me a 1 mile an hour savings, maybe 5? Is it, what am I looking at? And so each of those will be live linked to their own strategy sheet. And as I mentioned, this product will be published in about a month, so stay tuned for some more emerging tools from NCDOT. And hopefully I got under my 5 minutes, and I'll turn it back over to Matt for questions.
Yep, we have time for one question.
One question.
Yeah, I just want to say they've done a great job getting this set up, and I'm really hoping to get input from all the DOTs and consultants to improve upon this and maybe do a pooled fund study at some point and just make this better and better. So, anyone have a question?
I had a question. About your hydroplaning, what started that motivation in the first place? Was there a lot of accidents happening because of hydroplaning, or was there just a vision that you had for many years, or?
So, we're from Raleigh, and Raleigh is just growing and growing. And I-40, they said we need to widen it. So they said, hey, we're going to 4 lanes. Whoa, that's a lot of pavement to cross. So we had to think of, what do we need to do? Because water film thickness is going to be a problem. And so we did have some old tools in the past that used Galloway's equations to check for hydroplaning. And so we knew that there was going to be a problem. And so that's why we did some geometric changes, like breaking the inside lane to the median. And we were going to an 0.25 cross slope. But those things didn't really mesh well with the green book, because when we were braking to the median, we were doing 0.25 one way and 0.25 the other way, and that people were not happy with the 0.5 rollover. So we really got more involved in this in the RFPs on design build projects, because we wanted them to make sure that we were checking for this. And so it just blossomed into what it is, and it's just become my passion.
All right, thank you. Everybody give a round of applause.